Hello physics fans, today we're going to be discussing Ampere's law and finishing up our material on dipoles. You'll remember from last week that we have 3 right-hand rules so far. We're going to get a new one today. The first right-hand rule is that if your particle is moving at the speed v, that's your index finger, in a field, a magnetic field that's pointing in the direction of your middle finger, then your thumb is supposed to be perpendicular to both your index and your middle finger, and that will be the direction of the magnetic force. Okay, so that was last week. We also learned that currents are the cause of magnetic fields, and we learned about the example of a long straight wire. In that case, your thumb is pointing in the direction of your current, and then your fingers are supposed to be at a right angle to your thumb, to this direction, and pointing in the direction of the field that's looping around the current. Then finally on Friday we talked about how if you take a loop of wire and you curl it around into a circle, that gives you a pretty reasonable approximation of what's going on in a individual magnet. And so this is the dipole approximation for a permanent magnet or a little atomic magnetic component. And we model this as a little loop of current whose magnetic moment is pointing out, and if you curl your fingers around the loop in the direction of the current, your thumb is going to be pointing out in the direction of the magnetic moment vector. The magnitude of this vector for an individual, for a bunch of loops put together, is going to depend on how many loops, so this is the number of loops, no units, times the current, so that has units of amps, times the cross-sectional surface area, so that has units of meters squared. Now, since it was the end of the week, last time we met, you did have a quiz, online quiz since then. The question that people had the most problems with was this one. It says a negatively charged particle is slowly moving as it enters a region that has a constant magnetic field. If the velocity of the particle is initially perpendicular to the magnetic field, what will be the subsequent motion of the particle? Well, that's this situation. So we discussed this a little bit in class on Friday. We have 3 cases that we should understand pretty well. We should understand the case where B and V are parallel. In that case, our F would be 0. And the reason is because of this force equals QV cross B rule. The magnitude of that force is going to depend on magnitude of Q, magnitude of V, magnitude of B, times the sine of the angle between the two. So if V and B are parallel, the angle is 0, and that sine of the angle gives you a force of 0. If you have V and B, for instance, like V is in this direction, B, if you have a plus charge, and B is out of the page, V cross B would give you F in that case. let me draw it so it's consistent with the picture here. B is into the page. If I had a plus charge, V cross B would give me F. So my plus charge would be going around in this direction. My minus charge would be going around the other direction. Okay, so in that case, we would get motion that would follow a circular path in the magnetic field to the magnetic field lines. And then if you have the case where your B is up here and then, your B is pointing up and then your V is pointing at some angle, what you would get is that along the direction of B, that V parallel doesn't change, but the V perpendicular is constantly changing direction, and your path becomes that of a helix. Okay, so those are three cases to keep in mind. Now, the other thing that we introduced on Friday was the idea of a magnetic dipole. We've talked a little bit about this already today. And the two things I want you to remember about magnetic dipoles is that they are both targets of and sources for magnetic fields. So just as with electric fields, charges could be pulled on by electric fields and they could produce electric fields. Here we have magnetic dipoles, so these are little current loops. If we put a magnetic dipole in an external magnetic field, it experiences a torque. A torque causes something to spin. So on Friday we talked about how this sort of effect can easily explain what's happening in a DC motor. We also talked a little bit about, or actually I don't think we got to this. So we're going to talk today about how for this type of configuration, if you have a loop of current and you get far enough away from it, along the axis it's going to die off as 1 over z cubed. So you'll remember our Coulomb's law is 1 over z squared. Our electric field for an electric dipole died off as 1 over z cubed. So we have the same type of behavior here where our magnetic dipole has a magnetic field that dies off as 1 over z cubed. So we're going to see that in just a moment. So first I want to remind you, how does this work? Why do magnetic dipoles experience a torque? Well, a torque is going to cause something to spin, so I'm going to redraw the diagram that I drew in the video from Friday. In this one, I want you to imagine we've got a loop of current. It's going into the page, so just bear with me. This one's behind the other one. So there's our loop of current. That's our I. If I have put this into a external field, B is pointing like this. There's my B. Now I can use my right hand rule and figure out what direction the mu is pointing. In this picture, the mu would be pointing out like this. Okay. Then I should be able to figure out from mu cross B. So my mu is my index finger, my B is my middle finger, equals the direction of the torque. Mu is this way, B is up, and then my torque would be out of the page. Now what does that mean? Why is that going to cause this loop to spin, to start having some angular acceleration? Well, if you look at it here, this I and this B are parallel. So on this, on the side of the ring that's closest to us, there's not going to be any magnetic force. However, on the top, the current is going into the page, and so at the top it's going to be V cross B is F. So at the top of the page, the F would be pointing in this direction. At the bottom of the page, the current is coming, so I guess I'll draw that. I is going into the page. At the bottom, I is coming out of the page. And so if you use your right hand rule, you'll figure out that F is pointing the opposite direction. And so you can see how pushing on the top of the ring in one direction on the top and the other direction on the bottom is going to cause that ring to spin. So that's the idea here. Torque is causing an angular acceleration, and the direction of the torque is the direction of the magnetic, the angular acceleration. Let me just make sure that I've got that correct. Mu cross B gives me torque. Okay, I think that's right. I might I might have it slightly. I cross B gives me F. Okay, I is coming out of the page. Cross B gives me F. Okay, mu cross B gives me torque. Okay, I think I've got that picture right. Let's do a quick problem with this. If we've got a circular loop of radius r, so our r equals 0.15 meters, carries a current of 2.60 amps. Okay, current is I. It is placed so that the normal to its plane makes an angle of 41 degrees with a uniform magnetic field of magnitude 12 Tesla. Okay, extremely unrealistically big magnetic field. But our picture here is that we have a magnetic field, and then our magnetic moment pointing out normal to this surface is at an angle of 41 degrees. Okay, so then I have two parts of this problem. Part A says calculate the magnitude of the magnetic dipole moment of the loop. Okay, so remember the magnitude of the magnetic dipole moment is number of times the loop goes around times the current times the cross-sectional surface area. So in this case, the magnitude of that mu is going to be n, and it just tells us that it's one loop, so n would be 1 in this case, times I, so that would be 2.60 amps, times the surface area of that loop. So if its radius is 15 centimeters, area is pi r squared. So pi, so I'll just write it in explicitly, right around 3.14 times 0.15 meters squared. Okay, so put that in your calculator, 2.60 times 3.14 times 0.15 times 0.15, and you should get something right around 0.184 amps times meters squared. So that gives you the magnitude of that mu, of that dipole moment of that particular loop. Then part B asks, what is the magnitude of the torque acting on the loop? So in this case, you'd have to use torque is mu cross B. So you'd need the magnitude of mu, you'd need the magnitude of B, and you'd need the sine of the angle between those two vectors. So in this case, it would be torque is equal to this number, what you found for the magnitude of the magnetic moment, 0.184 amps meters squared. And then you would take it times the B that they gave us, 12 Tesla, and then you would take that times sine of 41 degrees. Okay, and you put all that in and you would get 1.45 newtons times meters, because you remember from last semester, torque is also R cross F, and the reason that we liked that vector is that we could relate it to the angular acceleration by t equals I and times the angular acceleration in radians per meter squared. Now notice, unless we knew the moment of inertia of this particular loop, we could not solve for the angular acceleration just yet. So there's sort of a gap in some of these problems. All right, now, so that's how your magnetic dipole can be acted upon by an external field. Now, we can also use a magnetic dipole or an ensemble of them as the source of the magnetic field. Now, you'll remember if you watched the last video that we can use this rule called the Biot-Savart law to calculate for any group of currents that's stable. You can calculate the magnetic field. So Biot-Savart law is the fundamental rule of magnetostatics, sort of the same way that the Coulomb's law was the fundamental rule of electrostatics. But it's quite hard to apply. And if you do apply it, I'm not going to do it in this video because I'm not sure how illuminating it would be. You can find an exact solution for this case, and it simplifies pretty nicely along the z-axis. If you have a current loop that's going around like this, the B is ultimately going to be pointing up because the contributions of the field from these the different currents on each side of the loop, the parts that are pointing horizontally are going to cancel out from the different sides of the loop pointing in different directions. And then the parts that are pointing out or into the loop are going to, along the z-axis, they're going to add constructively. So this expression here, it includes I, that's the current going around the loop. It includes R, that's the radius of the loop itself. And it includes Z, which is how far the point of interest where you're actually measuring the magnetic field, how far away from the loop you are. Now, this expression is already not so bad to work with. It's even nicer, though, if you go far away from the loop. If Z is much bigger than R, then we can get a nice approximation, where now we can write the magnetic field in terms of Z, how far away we are, and mu, the magnetic moment. Now let's just see how that works. Here's our exact analytic expression for B that we would get if we apply the Biot-Savart rule. Now, let's make an approximation. If R is much, much bigger than Z, R squared plus Z squared is going to look approximately just like Z squared. Okay, because, or sorry. Yeah, no, that's right. I have this backwards though. If Z is much bigger than R. So we're thinking little loop, we're quite a far distance from it. So if Z is much, much bigger than R, then that R squared plus Z squared approximately just looks like Z squared. In that case, my B along the z-axis looks approximately like mu naught times I, and I'm going to write in pi r squared. Okay, so I put an extra factor of pi up here, and then I'm going to put an extra factor of pi down at the bottom. So I sneaked in an extra pi there. And then my r squared plus z squared, I'm just going to put in z squared because I can ignore that r squared if it's much smaller than z squared. So this is going to be z squared to the 3 over 2 power. Now, I want you to notice something. This right here, this I times pi r squared, this is your I times your cross-sectional surface area. And mu naught is just a constant. And so what you can write then is that this B is approximately equal to mu naught over 2 pi. And then this is the magnitude of the magnetic moment, I times the surface area. And then if you take z squared to the 3/2 power, 2 times divided by 2 is 1, so this is z cubed. All right, so there you go. That shows us how we're going from this loop model, and we're going to get a magnetic field that looks approximately like this. Okay, so the magnetic moment is pointing up like this, and your B is constantly changing direction, but its magnitude is approximately related to 1 over z cubed, and above the magnetic dipole, it's pointing away, and then below the magnetic dipole, the magnetic field is pointing toward. So let's do a quick example of this. It says a student makes a short electromagnet by winding 300 turns of wire around a wooden cylinder of diameter 5 centimeters. Okay, so here our N is 300. That's how many times the wire goes around. And the diameter is 5 centimeters, so the radius would be 2.5 centimeters. So R here is 0.025 meters. It says the coil is connected to a battery producing a current of 4 amps in the wire. So our I would be 4 amps. The first question it asks then is, what is the magnitude of the magnetic dipole moment of this device? Well, you can just multiply these together and you can easily get the answer. It would be 300 times pi r squared for the area. Oh, let me put it in terms of the equation. 300 is N, I would be 4 amps. And then your pi r squared would be 3.14159 times 0.025 meters, and then that one would be squared. Okay, so it's easy to put those numbers in, and you would get around 2.4 amps times meters squared. So that's part A. Now part B on this example asks, at what axial distance, where z is much bigger than d, will the magnetic field have a magnitude of about 5 microtesla, about 1/10 of the Earth's magnetic field? Okay, well in this case you could use your expression here, where they've already told us that the axial distance is much bigger than that 2.5 centimeters. So let's look. If you have B that you've been given, B is 5 microtesla, so 5 times 10 to the minus 6 Tesla. What you would like to solve for is asking at what axial distance. So you want to solve for Z here. So if you have B equals mu naught over 2 pi, mu naught's just that number, times mu over z cubed. This would then, if we solve for z, give us z cubed equals mu naught over 2 pi mu over b. And then I can take each side to the 1/3 power. take the cube root of each side. And then I could go ahead and stick in numbers here. So this would be 4 pi times 10 to the minus 7th, and that has units of, this is mu naught, as units of Tesla times meters over amps, and then that's divided by 2 pi. And then I would take it times the 2.4 amps meters squared that I found here, 2.4 amps meters squared. And then I would divide it by B, that 5 times 10 to the minus 6 Tesla. Okay, so what would I find? Oh, and I'm going to take that to the 1/3 power. So amps would cancel out, Teslas cancel out, and I get meters times meters times meters, so that's meters cubed, and then I'm taking the whole thing to the 1/3 power. And if I just plug all of that in, I should get Z equaling about 0.46 meters, or an answer of 46 centimeters. Now, I do want to warn you, on your homework, I gave you an example that's not quite as simple. You'll remember when I did the demo in class of having a couple of loops of current and then putting a bulb in the middle where we got the electrons to go around in a ring. These rings were causing the magnetic field, and I said, I haven't told you why yet, but I will tell you. So this is the example where you get to work out the magnetic field in the center. This is a Helmholtz coil. So each one of these coils is producing a magnetic field. It says we've got an arrangement known as a Helmholtz coil. It consists of 2 circular coaxial coils, each of 200 turns. So each one of these has N equals 200. This one also has N equals 200. And radius of 25 centimeters. So R equals 0.250 meters, separated by a distance of S equals R. So this S is also 0.250 meters. Then it says the 2 coils carry equal currents of 12.2 milliamps. So I equals 12.2 times 10 to the minus 3 amps. In the same direction, find the magnitude of the net magnetic field at P midway between the coils. Now, one of the nice things about electrodynamics, in at least classical electrodynamics, it's a little bit more complicated once you go into quantum field theory and all that, but classical electrodynamics is a linear theory. So, what does that mean? It means if you find the solution for one loop, and then you put in 2 loops of current instead, you can just double the size. So you can add up the solutions to known things and get the solution to an unknown thing if you can put it in terms of things you know. So, for instance, this first loop, we know the sort of magnetic field one loop is going to cause, and so if we have 200 loops, we just need to take this times 200. And this first loop is going to have a magnetic field that's pointing in the plus x direction. And this loop on the right is also going to have a magnetic field that's pointing in the plus x direction. You can try that out with your right hand if you want. And so each one of these is going to have 200 times this. And then this one's going to have 200 times this. The thing to keep in mind, though, is your z in this case is going to not be 0.250. It's going to be half of that. Now, the reason I put both of these equations up here is that you might be tempted to use this second equation because because it's a little bit simpler. But in this case, we need to remember that this equation presupposes that your z distance is much, much bigger than r. And in fact, in this case, that is not a good approximation at all. The z is, in fact, less than r. So this, we don't get to use it. We have to use the expression, the analytic expression for our ring. And then for our z, we're going to use r divided by 2. And then we're going to have to multiply by 200 to get the magnetic field contribution over here, plus 200 times the magnetic field contribution of one loop over there. Okay, so essentially it's going to be 400 times this thing with z of, 12.5 centimeters. All right, so after all that talk, we're finally going to get to the new idea for today. All right, Ampere's law is essentially an analog to Gauss's law, except for currents and magnetic fields instead of for charges and electric fields. So what does it say? It relates the current piercing a surface, a surface, typo, to a line integral on the surface boundary. So what do I mean here? Well, if you have a loop, you can make a integral around all of these points, and there will be some magnetic field. This loop will have some contribution, so there would be your B3. This I2 would have some different direction of B2. My drawing is not great here. So you'd have a magnetic field contribution from this current 3. You'd have a magnetic field from the current 2. You'd have a magnetic field contribution from your current 1. Oops, do I have the right direction there? No, I don't. It's opposite that. There's your B1. Okay, in any case, so at each point along this path, you would have some net magnetic field that's the sum of all the magnetic fields from all the currents in your region. Now, the upshot of it is that if you integrate all the way around a loop, the contributions of a current that is outside of the loop will add up to 0 unless that current is inside of the loop itself. Okay, so just like in Gauss's law, we were taking a surface and then we could relate the flux to the sum of the charges inside of the surface. Here we're taking a line integral around a loop and we're relating it to the currents that pierce that particular loop. Now, something that's a little confusing is that we have yet another right-hand rule. And this is saying, if we consider the direction of integration to be in the direction of our fingers, so we're curling around this loop, the direction of our thumb is the plus direction for a current, and then the direction opposite our thumb is the minus direction. So let's just do a very simple, I know this is a little confusing. Hopefully it'll be clearer if we do an example. So here's a silly textbook example. This is not very useful yet, but it hopefully does give us a sort of a feel for what this rule is actually saying. So it says, this figure 2933 shows 4 identical currents I and 5 Amperian paths A through E encircling them. Rank the paths according to the value of this line integral taken in the directions shown, most positive first. So let's just look at how to do this mu naught times I enclosed. So for this first case, this would count if you do your loop around like this. Pointing up would be the positive direction for a current. So this current going down would count as a negative current. This one would count as a positive current. This one would count as a positive current. This one would count as a positive current. So if I do the I enclosed in this case, it would be -1, +1, +1, +1. So you get overall +2I. And that line integral would give you mu naught times 2I. Now you can do all sorts of weird loops. So in this case, if you're doing this loop as before, this would be minus, this would be plus, this would be plus. But now if we twist that loop such that our direction of the loop is going around like this, now, just for that last one, then that would count in this line integral as a minus. All right, so this is sort of a weird example, but it's just trying to get you to think about the right-hand rule for this particular case. So in this case, minus, plus, plus, minus, this line integral would give you a result of 0. Okay. If we're looking again here, this would be minus, minus, because our loop direction is going like this. So if we have a loop like this, those currents, the current is going this way, those count as negative currents for that choice of Amperian loop. So minus, plus, minus, minus, that would give you minus mu naught times 2I. Okay, in this case, this would be minus. And then, if we're looking at this loop here, let me make sure I've got this right. Whoops, I spoke too soon. So if we look here, this would count as a plus, plus, plus. And then we are going to be a little tricky and loop this around such that the loop is going in the orientation of the loop is going to be in the same direction as the current going through it. So this would actually count as a plus for our Ampere's law rule. So this would give us mu naught times plus mu naught times 4I. And then in this case, let's draw our. Let's make sure we understand what's going on. Whoops, I confused myself here. Going around, I'm drawing my loops. And then I would go ahead and try to see, is that a plus? This one would be a plus. And then looking at the direction, this one would also be a plus. Looking at the direction, this one would be a minus. And then looking at the direction of the loop, this would be a plus. So this would be plus 1, minus 1, plus 1. Okay. So that would give me mu naught times 2I. Okay, so I know that's a little confusing, but it's just to try to get across to you that there is a right-hand rule sort of lurking inside of Ampere's law. Now at this point it might seem to you, well, why am I doing this? This seems confusing and hard. But I will remind you that the Biot-Savart law was itself confusing and hard. And so it turns out if you use Ampere's law, you can get to some of the classic results in magnetostatics really quickly. So for instance, it took us quite a bit of work to get from the Biot-Savart law to the expression for the long straight wire. We had to do some integrals and stuff. But I bet that we can do this derivation in so quickly when we have Ampere's law. So let me show you what I mean. Let's start out with the idea of a line of current. And let's have that line of current coming out. Now, you'll remember that my B field is directed kind of in a circle around this I. So there's your B field. So this is perfect for application to Ampere's law, because if I integrate around this circle, the B and the little dS's, the little line segments around the circle that I use, are going to always be in the correct order. So if I use this rule, B.ds, each one of these is going to be parallel to the orientation of the circle. If I go around the circle like this, using my Ampere's law right-hand rule. So this line integral just becomes B times, if this distance is r, times my circumference, so 2 pi r. Then on the other side of this rule, I would get mu naught times I enclosed, which in this case would just be that current. Remember, this is an infinitely long line of current, and we're just taking a line integral around one little section of it. And boom, I'm done. Mu naught I over 2 pi r. That's what we got from our Biot-Savart law after much sweat and tears. Okay, so it seems a little too cheap, but it is right, and there's a lot more vector calculus where that came from. Now, the real reason we want to introduce this is because we're interested in a particular type of object called a solenoid. And a solenoid is also going to be the model for the inductors, which I told you were the circuit element that we need to introduce in this unit. We already have capacitors, we already have resistors. We're going to have something called an inductor that stores magnetic energy the same way that a capacitor stored electric energy. So let's see what's special about an inductor, or sorry, about a solenoid. A solenoid is basically, look at this. What would happen if you took a bunch of loops and then you smushed them up against each other? Well, the magnetic field vectors add linearly. So if all of those field vectors are pointing in the same direction in the middle of the loops and you smush them together, it begins to look just like a constant magnetic field inside, and it turns out this and that effectively cancel out, so you get a zero magnetic field outside. Okay, and that's the idea of an infinitely long group of a spiraling charge, or sorry, a spiraling current. So if we use that, we can very easily find the equation for the magnetic field you would expect inside of a solenoid. So let's quickly, did I not give myself, well, I guess it doesn't take a lot of space. So in this case, using Ampere's law, all right, if we integrate the magnetic field around this loop, so we're like going inside the magnetic field and then coming out, this leg of the loop is going to have a zero contribution, because the direction of the path is perpendicular to the direction of the field inside. Outside, we're saying there's zero magnetic field, so this part of the top part of the path has zero contribution. The only part of the path that does contribute is this bottom element. Let's say that this has some length L. And so if there's a magnetic field B inside of that solenoid, the left-hand side of Ampere's law would just give us B times L equals, and then here I've got mu naught times I enclosed. So it'd be mu naught, and then I enclosed would be however many loops are inside of your box. Okay, so let's say that that is n loops. We count them up. You know, n could be, here it would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, so n would be 13 in that case. Well, what we can say then is just, and so it would be n times I. I is the current running through one of those loops. And so they're running helically like this. They're a bunch of spiraled loops pressed up against each other. So if we just divide both sides by L, we find that this is mu naught n over L times I. And the way that they usually write that is B equals mu naught, that's constant, times I, that's the current you run through your solenoid, times N. Now keep in mind, N has units of inverse meters because it's turns per unit length. I has units of amps, and then mu naught has units of Teslas times meters over amps. So if we're looking at the units on this whole thing, amps will cancel out, meters and inverse meters cancel out, and it is correct. So this is units of Tesla. So just to do the simplest problem we can, let's suppose that a solenoid that is 95 centimeters long, so L equals 0.95 meters, has a radius of 2.0 centimeters, so 0.02 meters, and a winding of 1200 turns. It carries a current of 3.6 amps. Calculate the magnitude of the magnetic field inside. So if we use this expression, we would just need to have B equals mu naught, so that would be your 4 pi times 10 to the 7th, 10 to the minus 7th, okay, times I times N. Now, if you are not keeping in mind what this means, you will be very tempted to just put in 1200 here. But remember, little n is actually code for number of loops per unit length. So this would actually be 1200 over 0.95 meters. Okay, so I'll let you calculate that out, but notice that you do not need R. R is flurf in this problem. It's trying to confuse you. So there are some interesting extra things that we're going to run into when you start thinking a little bit more broadly. So you'll notice in Ampere's law we're starting to calculate some sort of a topological property where you integrate around the loop and you can deform that loop all you like and you get the same result. Now, one of the best thinkers ever about electrodynamics was our friend and big physics daddy, Albert Einstein. And he made the very intriguing observation that if you go ahead and run up alongside of a current, so if a current is going this way, and you begin to move as fast as the electrons in that wire are moving, the magnetic field should disappear. Why? Because you don't have any current anymore. In that case, the magnetic field goes to zero, but you still have electric forces. And the electric forces, it turns out, are staggered in time and have exactly the same consequence as the magnetic field. So the fact that it takes time for those electric signals to propagate from one place to another mimics the magnetic field. So it turns out B and E are sort of the same thing. And so that's why I was a little bit grouchy when I introduced the magnetic fields and said they have different units from electric fields. That's true in SI units, but since you can convert B into E and E into B depending on how fast you're going, we should be a little suspicious about this. And Einstein famously imagined himself traveling along a wave of light using Maxwell's equations and realized that even time and space can be traded off within Maxwell's system, and that consideration of electrodynamics led Einstein to relativity. Now, it's also interesting that looking at magnetism also was one of the key things that led to taking quantum mechanics really seriously. The electron itself has, instead of just having a magnetic moment that can be infinitely malleable in terms of its direction, the electron has what's called a quantum magnetic moment, which you usually hear described as the spin of the electron. Okay, now the electron acts as a sort of like a magnetic dipole in that you can put a torque on it and change its direction. But what's a little bit funny is that instead of acting just like a classical dipole, that magnetic moment, when you measure it in a really strong magnetic field that's inhomogeneous, so that means it's not the same going right to left. Instead of just splitting the path of the electron into a smear like you would expect from the classical prediction, it turns out you have to use quantum mechanics to predict probabilities of the electron going up or down. So this is a very famous quantum experiment called the Stern-Gerlach experiment, and it led people to sort of doubt whether this classical picture of magnets is quite right in the end. But in this course, we're going to stick with classical magnets for a while. And so in lab this week, you're going to use a magnetic field sensor to measure the dipole moment of a neodymium magnet. And then you're going to measure the current versus the magnetic field by sticking the magnetic field sensor inside of a solenoid and then turning up the current and noticing how B gets bigger as the current gets bigger. Okay, so we're getting there. Today we talked about how magnetic dipoles can be acted upon as by magnetic fields. The torque causes them to gain some angular acceleration, or they can be used as a source of magnetic fields. Then we talked about Ampere's law. Ampere's law is like Gauss's law was for electrostatics, where we could add up the flux over a surface and get relate it to the charge inside. Ampere's law is about a line integral around, and it tells us about the currents that pierce through. And then finally, we used Ampere's law to help us find the magnetic field inside of a solenoid, and these solenoids are great because they allow us to create a magnetic field that's relatively constant within the middle. Okay? So thanks for watching, and I'll see you soon.